Hello there, and welcome to the Sleep Porch. Tonight, we are drifting into the quiet brilliance of diamonds. Objects so familiar that we rarely pause to consider how extraordinary they truly are. These small, shining forms carry stories that begin far beneath our feet, in places shaped by pressure, time, and patience beyond our imagination. They are symbols of celebration and devotion, yet they are also archives of Earth's deepest processes, waiting quietly to be seen. As we move through this topic together, you may begin to view diamonds in a new way, not simply as adornments, but as travelers, survivors, and witnesses to the forces that continue to shape our planet. There is something grounding in that idea, that something so calm and steady was born under such extreme conditions and still emerged with such quiet beauty. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here as well, one sleepy soul at a time. But for now, all you need to do is unwind. Let your shoulders relax. Allow your eyes to grow heavy, and let your thoughts soften as we wander through this remarkable world together. Let's begin. Volcano-like eruptions can deliver diamond to the surface with astonishing speed. The word eruption makes us think of lava, but diamond delivery is stranger than that. In rare events, gas-rich magma punches upward from deep regions, racing through the crust so quickly that it can carry solid chunks like a freight elevator. This speed is crucial. Diamonds are stable only under immense pressure, so a slow rise would give them time to transform into other forms of carbon. Instead, a rapid ascent acts like a rescue mission, preserving crystals that would otherwise be erased. When the eruption ends, it leaves behind a vertical pipe of unusual rock and scattered fragments called xenoliths, pieces of the deep brought to the surface like souvenirs from an unreachable place. Much later, erosion and rivers can spread those diamonds even farther, turning a single violent moment into centuries of quiet discovery. That is why some diamonds are found far from any obvious volcanic mountain. Their journey was not gentle, but their arrival can be. Slipping into soil, gravel, and stream beds, waiting for a human hand to notice. Most diamonds are even older than dinosaurs, by a lot. Dinosaurs feel ancient to us, that a diamond can make them seem recent. Many natural diamonds formed so far back that the continents above them were arranged differently, and the air and oceans were not what we know today. A diamond can exist through eras when life on land was barely getting started, through periods when ice covered huge portions of the planet, through times when tropical forests grew in places that are deserts now. That endurance gives diamonds a strange emotional weight. They are not just rare, they are patient. Their surfaces may be polished by human hands, but their cores are records of deep time. Even the tiniest crystal can be a relic from a world that no longer exists, carried into our present by a chain of events that had nothing to do with beauty or romance. When someone calls a diamond timeless, it is not only a compliment. It is a literal description of how long it has already been here. A diamond can trap ancient mantle minerals like time capsules. During growth, a diamond can swallow tiny crystals from its surroundings and seal them inside like insects in amber. Except these guests are minerals from the deep earth. Once trapped, they are protected from weathering, water, and the chemical chaos of the surface. That is what makes them so valuable to science. Many mantle minerals do not survive the journey upward on their own. They change, react, or fall apart. Inside a diamond, they can arrive intact, still carrying the signature of the environment that formed them. Researchers can study those inclusions to learn about temperature, chemistry, and the conditions of deep rock using the diamond as a natural vault. For a viewer, the wonder is simple. A gemstone can be more than pretty. It can be a sealed sample bottle from a region of Earth that no drill has reached. When you look into a clear stone and see a tiny crystal, you are not seeing a floor. You are seeing a preserved fragment of the planet's interior, saved by chance and crystal growth. Those trapped minerals reveal pressures humans cannot create easily. Some inclusions carry an almost unbelievable clue. They form at pressures so high that recreating them in a laboratory requires specialized equipment and extreme conditions. When scientists identify certain mineral phases inside diamonds, they are effectively reading a depth gauge. These minerals act like witnesses that cannot lie, because their crystal structures only exist when pressure is immense. If the pressure drops, they would normally transform into different forms. The diamond prevents that change by keeping them locked in a tight embrace. That means a tiny inclusion can point to formation zones far beneath the crust, sometimes hundreds of miles down, where Earth's internal layers shift in ways that shape the planet's behavior. This is not abstract trivia. Pressure changes how minerals hold water, how rocks flow, and how heat moves, which affects everything from volcanism to the long cycle of continents. A diamond inclusion is a miniature report from that realm. It tells us not just that diamonds are deep, but that some are born in places where matter itself behaves differently under force. Diamonds are pure carbon, yet they behave like living light. What changes everything is the way those carbon atoms lock hands. In a diamond, each atom bonds to 4 neighbors in a rigid 3-dimensional scaffold, more like a perfect architectural truss than a pile of charcoal. That crystal order gives diamond its clarity, its stiffness, and its strange relationship with light. Photons enter, slow down, bend, and ricochet through the interior, as if the stone has its own private hall of mirrors. Even when a diamond looks still, the physics inside is busy, turning ordinary illumination into sharp flashes and tiny rainbows. Carbon can also arrange itself as graphite, the soft material in pencils, which makes diamonds feel like a reminder that matter has moods. The same element can write on paper or outlast mountains, depending on how it decides to connect. A diamond began deep underground, long before humans existed. A finished gem can feel like a modern object, but its story starts in darkness, far beneath the continents, where rock behaves more like slow-moving putty than solid ground. There, carbon atoms drift through hot fluids and melts, then settle into crystal form in a place no sunlight has ever reached. What is most unsettling is the time scale. A diamond can spend unimaginable stretches of time resting in the deep, while oceans open and close above it, while mountain ranges rise, wear down, and vanish again. It is not waiting for us. It is simply the crysting. Only much later does a violent geological event carry it upward where humans find it and give it a name, a price, and a story. When you hold a diamond, you are touching a survivor of Earth's long memory shaped before our species had a plan or even a word. Diamonds are the hardest natural mineral commonly found on Earth. Hardness is not toughness, and that twist is part of what makes diamond so fascinating. Hardness means resistance to scratching, and diamond sits at the very top of the standard scale used by gemologists because its crystal lattice is so tightly bound. That tightness makes it stubborn against abrasion in a way that feels almost unfair. A diamond does not simply resist wear. It forces the world to yield first. This is why tiny diamond grains are used to shape materials that would defeat most tools, and why a diamond point can leave a mark where others slide away. Yet this extreme hardness comes from order, not invincibility. The same internal perfection that makes diamond so scratch-resistant also creates directional weak planes, like hidden seams in a fortress. Nature built the hardest common mineral by building it beautifully, then quietly leaving it with one precise way to fail. Some diamonds formed more than 100 meters underground. That depth is not just a distance, it is a different kind of world. Far below the surface, pressure climbs until rock behaves in ways that defy everyday intuition. Cracks narrow. Minerals rearrange and fluids move through stone like whispers through a wall. In that environment, diamond becomes the preferred form of carbon, and crystal growth can begin. What makes this fascinating is the journey required to bring such a stone upward. Diamonds do not slowly drift to the surface like bubbles. They need a rapid geological elevator. A violent event that tears through layers of earth and carries fragments upward before the crystals can change back into softer carbon forms. If the trip is too slow, the diamond can lose its identity. So each deep-formed diamond is evidence of both creation and escape. It was born in crushing pressure, then saved by speed. When you see one glittering under room light, you are seeing something that should never have been visible at all, except that Earth briefly moved fast enough to deliver it. One diamond can scratch nearly every other gemstone you know. Scratching is a simple test with a dramatic lesson. When two minerals meet, the harder one plows microscopic grooves into the softer one, leaving damage that never truly disappears. Diamond usually wins that contest, not because it is sharp, but because its atoms are locked into a structure that refuses to be carved by most rivals. This is why careful jewelers store diamonds separately, even from other precious stones. A loose diamond can quietly scratch sapphires, rubies, and emeralds simply by resting in the same pouch. This is also why diamond polishing is such a specialized skill. To shape a diamond, other diamonds are usually crushed into powder because the material effectively requires its own kind to work it. There is something almost mythic in that idea. A stone capable of marking nearly everything else is, in practice, most easily shaped by a chorus of its own dust, slowly wearing it into brilliance. A diamond can withstand fire, yet it can still burn. Diamonds feel eternal, which is why many are surprised to learn they are not beyond destruction. Under everyday conditions, however, they remain stable. But under intense heat, especially in the presence of oxygen, diamond can oxidize. In plain terms, it can burn. The reason is simple and unsettling. A diamond is carbon, and carbon can react with oxygen when the temperature is high enough. That does not mean a candle with a razor ring, but it does mean that jewelry can be damaged by extreme heat, in a workshop fire, a torch accident, or careless repair. Even when a diamond does not fully burn, heat can cause changes that affect appearance. Metal settings can warp, stress can travel through the stone, and tiny fractures can worsen. The lesson is not fear, it is respect. Diamond's reputation comes from what it resists, but its chemistry still belongs to the same world as charcoal and smoke, with the same fundamental rules quietly applying. River gravels can hide diamonds carried far from their birthplace. Some of the most famous diamond finds did not come from hard rock mining at all. They came from patient water. Over long stretches of time, rain, wind, and flowing rivers break down diamond-bearing rocks and sweep the tougher fragments downstream.
Diamonds, dense and durable, can settle into natural traps. The inside bends of rivers, gravel bars, and ancient stream beds now far from any running water. This is why a person can discover a diamond in sediment with no obvious pipe nearby. The original source may be many miles away, worn down and disguised by erosion. These deposits can be wonderfully deceptive. A river can sort and concentrate stones the way careful hand might, turning a scattered supply into a pocket of treasure. It also creates mystery. If you find diamonds in gravel, the next question is not just where they are, but where they came from.
The landscape becomes a detective story written in pebbles, currents, and time. A diamond's growth can happen in pulses, not one moment. It is tempting to imagine a diamond forming like a single magical event, but many do not grow that way. Growth can start, pause, and start again, depending on whether the surrounding conditions provide carbon-rye fluids or the right chemistry for crystal building. These episodes can leave subtle internal boundaries, like chapters where one phase of growth ended and another began later. The result is a stone that is not just old, but complicated, with a history of changing circumstances written into its interior. This makes diamonds feel less like static objects and more like records of shifting environments deep underground. One pulse might occur during a period of mantle fluid movement, another during a later event that reintroduced carbon and pressure conditions that favored diamond. Again, the pauses matter as much as the growth, because they hint at a deep world that is not constant. When you see a diamond as something that assembled itself over time in fits and starts, it becomes easier to feel the planet as active, even in places we call solid. A diamond can be a timeline, not a snapshot. Many diamonds grow as crystals, but some grows twins. Crystal twins are one of nature's most elegant shortcuts. Instead of a single, orderly crystal expanding smoothly, two parts of the diamond grow together in a specific mirrored relationship, locked into each other's orientation. This can create unusual shapes and internal patterns that are not mistakes, but expressions of how the crystal found a stable way to expand under its conditions. Twinning can also influence how a diamond behaves during cutting. A cutter may discover that the stone has directional quirks, subtle variations in strain or growth behavior that require different planning than a simple crystal. For viewers, the fascination is in the idea of identity. Two diamonds can be the same material, formed under similar pressures, yet one is a straightforward crystal, and another is a paired structure that grew in partnership with itself. It is like finding two versions of the same story. One is written in a single clean line. The other is written in mirrored paragraphs that meet in the middle. Twinning reminds us that even in the deep earth, growth is not always uniform. Sometimes it is cooperative, symmetrical, and strange in the most beautiful way. A tiny flaw can decide a diamond's entire personality. Perfection is not always the most interesting thing in nature, and diamonds prove it. Inside, many stones are tiny features, a minuscule crystal trapped during growth, a faint internal line, a cloud of microscopic pinpoints. These are not always damage. They can be fingerprints of formation, clues about the environment that built the stone. And yet, the market treats them as destiny. A nearly invisible inclusion can change a grade, shift a price, and decide whether a diamond becomes the centerpiece of a ring or disappears into an industrial tool. Even when you cannot see the feature without magnification, it can change how light moves through the crystal, subtly affecting the diamond's look. There is also a human story here. People often fall in love with the idea of flawless, but many collectors prefer stones with distinctive quirks because they feel like individuals, not copies. A diamond's personality is not always about being pure, it is about being specific. A tiny internal detail can turn a stone into a one of one. Most diamonds contain inclusions, tiny internal features from formation. What many people call imperfections are often the most honest parts of the stone. Inside a diamond, inclusions can appear as pinpoints, clouds, faint lines, or tiny shapes that seem like they were drawn with a single careful touch. These features are not decorations added later. They are the record of a crystal growing in a real environment, where the world does not pause for the sake of beauty. Inclusions can also change how a diamond feels to the eye, making it look softer, brighter, or more complex, depending on where they sit and how light interacts with them. Some are so small they only appear under magnification, yet they still influence the diamond's character, almost like a hidden accent in a voice. The most captivating part is that inclusions make each stone unrepeatable. Even diamonds with the same shape and weight can be distinguished by their internal landscape. It turns a gemstone into a document, not a duplicate. Some inclusions are other crystals locked inside forever. Sometimes, a diamond carries a guest, and that guest has a name, a shape, and its own story. Under magnification, you can find tiny crystals trapped inside, complete with sharp edges, colors, and reflective faces like a miniature museum exhibit sealed behind glass. These are not stains or surface marks. They are separate minerals that were present during growth and became enclosed as the diamond expanded around them. This is a rare kind of intimacy in geology. One crystal literally wrapping another and keeping it unchanged while the world above transforms. For gemologists, these trapped crystals can help identify origin and growth conditions. For anyone else, they offer a more personal thrill. You are not just looking at a gem, you are looking at a stone that contains another stone, perfectly preserved, impossible to remove without destroying the whole. It is a reminder that diamonds are not only objects of sparkle, they are containers capable of holding a private secret for a span of time that makes human history feel brief. The famous 4 C's grade diamonds: cut, color, clarity, carat. These 4 categories sound simple, but they are really 4 different ways of describing how a diamond behaves in the real world. Cut is performance, the way the stone handles light. Color is mood, the subtle temperature of its appearance. Clarity is identity, the presence of internal features that make it unique or make it cleaner. Carat is weight, the physical amount of diamond you are carrying. What makes the 4 C's captivating is that they constantly trade against each other. A heavier stone might be less lively if the cut is compromised to keep weight. A very clean stone might still look dull if the proportions waste light. A slightly warm color can look beautiful in the right setting and lighting, while a colder stone can feel sharper and more formal. The 4 C's are not a scoreboard, they are a set of levers. Changing one often changes how the others matter. Understanding them turns diamond shopping from guessing into noticing, because you start to see what your eyes respond to and why. Carat is a weight unit, not a size promise. Carat sounds like it should describe how big a diamond looks, but it only tells you mass. 2 stones with the same carat weight can appear very different in size because of shape, cut proportions, and how weight is distributed through the depth. A diamond cut too deep can hide weight where you cannot see it, leaving a smaller face-up look than you expected. A well-proportioned stone can spread its weight in a way that reads larger from above, even without adding mass. This is why experienced buyers talk about millimeter measurements and face-up dimensions, not only carat. It is also why certain shapes can look larger for the same weight, simply because their outlines cover more surface area.
The fascination is that carat is a number that feels emotionally powerful. Yet the eye does not read weight directly. The eye reads area, brightness, and presence. Carat tells you what you are holding. Cut tells you what you will actually see. Two diamonds can share carat weight, yet look wildly different. Imagine two stones that weigh the same, yet one seems to command the room and the other seems modest. This can happen because visual impact depends on more than mass. A shallow stone can look wide, but may lose brightness if light leaks out. A deeper stone can look smaller from above, but may appear darker or more concentrated in its pattern. Shape matters too. An elongated oval spreads across a finger differently than a round, changing the sense of scale even at equal weight. And then there is the subtle influence of edge thickness, girdle choices, and how high the stone sips in its setting. All of this means carat is only one part of the story of appearance. The same weight can wear like two different personalities, one bold and one restrained. This is why diamonds are such persuasive objects. They make you confront how perception works. We believe we are seeing size, but we are really seeing geometry, light behavior, and proportions working together. A diamond can teach your eyes to become more honest about what they value. Clarity grades judge internal features, not the diamond's beauty alone. A clarity grade is a careful description of what can be seen inside a diamond under standardized magnification and lighting. It is not a direct gauge of how beautiful a stone will feel to someone simply enjoying it. Many inclusions are impossible to see without a loupe, especially once the diamond is set and catching everyday light in motion. Others may be visible yet not unattractive, depending on their placement and how they interact with reflections. This is where clarity turns a bit philosophical. A very high clarity grade can be exciting because it suggests purity and cleanliness, but a slightly lower grade can still look breathtaking, and sometimes it brings more character at a lower cost. Clarity grades also cannot predict personal taste. Some people are drawn to the idea of near perfection. Others care more about brightness and cut. Clarity is best understood as a map of internal landmarks, not a final verdict on beauty. A diamond is a performance piece, and clarity is only one note in the music. Many diamonds travel upward inside rare rocks called kimberlite. Kimberlite is less like ordinary volcanic rock and more like a geological courier built for speed and surprise. It forms deep enough to pick up diamonds and odd fragments of the mantle, then rises in a rush that cracks the crust like a sudden heartbeat. When it reaches the surface, it can leave behind a carat-shaped pipe, a vertical pathway where the rock cooled in place. What makes this so captivating is how specific the conditions are. Most magma would melt, damage, or simply fail to carry diamonds at all. Kimberlite is unusually rich in gases and volatiles, which helps it move fast and tear loose passengers along the way. That is why a kimberlite pipe is not just a deposit, it is a story of transport. Miners are not digging for a gemstone alone. They are excavating the remains of a rare earth event that briefly connected the deep interior to open air. Some diamonds arrive through lamprey, a different deep eruption route. Lamprey is the quieter cousin that still carries astonishing gifts. It is rarer than kimberlite, and it forms from a melt with a very different recipe, often rich in potassium and other elements that make geologists pay attention. When lamprey erupts, it can deliver diamonds too, but the clues it leaves behind do not look the same. The shapes of the pipes can differ.
The minerals in the rock are distinctive, and the regions that host lamprey can be unexpected. This matters because it changes how humans search. Entire diamond discoveries have happened because someone recognized the fingerprint of lamprite and realized the ground was whispering a different kind of possibility. There is something thrilling about that. Two separate deep pathways can lead to the same glittering result, like two hidden doors into the same underground vault. And because lamprey occurrences are uncommon, every diamond found this way feels like evidence of a rare and specialized journey that Earth does not perform often. Diamonds can form in Earth's mantle, not the crust. The crust is where we live, but it is not where most diamonds are born. Their origin is deeper in the mantle, a vast region of hot rock that slowly circulates beneath continents. In this hidden world, pressure is strong enough that carbon prefers to lock into diamond rather than remain in other forms. That fact alone changes how you think about Earth. The mantle is not a silent layer. It is an engine room, moving heat, shifting continents, and storing chemical stories from earlier chapters of the planet. When a diamond forms there, it is not growing in a neat cavity like a geode. It is crystallizing in an environment that can include fluids, melts, and shifting conditions, all under crushing pressure. That makes a diamond less like a simple gem and more like a message from a place we will never visit directly. The mantle rarely speaks to us in solid objects. Diamonds are among the few times it does. Some diamonds contain water-bearing minerals from deep earth. Water feels like a surface story, but deep earth can hide it in unexpected ways. Certain diamonds carry inclusions of minerals that hold water within their structure, not as liquid droplets, but as hydroxyl groups tucked into crystal lattices. This is thrilling because it hints at vast, hidden reservoirs, water locked into rock far below ocean and clouds. When those minerals are found inside diamonds, they suggest that water can travel deep through subduction and be stored in mantle regions for very long times. That changes the mood of the planet. Earth is not simply a wet surface wrapped around dry rock. It may be a world that cycles water through its interior, using pressure and mineral chemistry as storage. The diamond becomes a messenger again, carrying proof that deep rock can keep water in forms we do not see. For the listener, it is a gentle shock. The same gem people prize for sparkle can also be a clue that Earth's water story has chapters far beneath our feet, written in minerals and locked away until a diamond arrives to reveal them. Certain diamonds prove parts of the mantle recycle old ocean crust. Some diamonds carry a chemical accent, but does not sound like the deep mantle at all. Their carbon and trapped minerals can show signatures consistent with material that once lived at the surface, then traveled downward with subducting tectonic plates. In other words, pieces of ocean crust, altered by seawater and life, can be pulled into the deep and eventually become part of the environment where diamonds grow. That is a staggering loop. It means the mantle is not an untouched abyss.
It is a mixing bowl that can receive ingredients from the surface and hold them long enough to reshape them. Diamonds, in this sense, are not just deep objects. They are proof of recycling on a planetary scale. A stone worn on a finger can carry echoes of ancient seafloor pushed down through Earth's conveyor belt and transformed under pressure into something entirely new. It also adds emotion to geology. The planet does not discard, it repurposes.
Diamonds can be the end of a journey that began with waves and basalt, then disappeared into darkness, only to return as a crystal that catches light. The sparkle comes from light bouncing inside, not surface shine. A diamond's magic is not a glossy coat. It is a carefully engineered escape trick. Light enters the stone and hips internal surfaces at angles that make it bounce back inward instead of leaking out. With the right geometry, those bounces send light ricocheting around until it finally bursts back through the top in bright flashes. This is why the same rough crystal can look dull in one cut and breathtaking in another. The cutter is not decorating the surface. They are designing a pathway for trapped light. That is also why a diamond that is too deep can look dark, and one that is too shallow can look watery. The balance is delicate, and it turns the gem into a tiny optical machine. When people say a diamond sparkles, they are really noticing a choreography of angles. It is less like paint and more like architecture, built to make light do something it would not normally do. Perfect detailer diamonds are rarer than most people assume. Clarity is a strange kind of rarity, because it is not about size or color. It is about what did not happen. Deep underground, a diamond is growing in an environment full of opportunities for interruptions, stray crystals, tiny fractures, and chemical changes. A truly clean interior means the diamond managed to form without swallowing much of its surroundings, and without being stressed in a way that left visible marks. That is why the most transparent stones can feel almost unreal, like a window cut from solid time. But the most interesting part is how quickly the idea of perfect can collapse into human limits. Two people can look at the same stone and see different things, depending on lighting, magnification, and experience. Clarity is not only geology, it is perception. When you realize how many chances there were for a diamond to carry evidence of its past, a clear one stops to feel like an improbable quiet victory, not just a pretty purchase. A feather inclusion looks delicate, yet it is trapped stone. The name sounds gentle, but the reality is pure geology. A feather inclusion is a tiny internal fracture that reflects light in a way that can resemble a soft, wispy shape. It is not a floating strand, it is a crack frozen in place, often formed when the crystal experienced stress during its long life underground or during the violent trip upward. What makes it so fascinating is the contrast between appearance and meaning. The feature can look airy and harmless, yet it represents the moment the diamond was pushed beyond comfort, then survived anyway, depending on its size and location. A feather can be nearly irrelevant, or it can change how a stone handles during cutting and setting. That gives it tension, like a quiet fault line. In some diamonds, a feather becomes a signature mark, a detail that helps experts recognize the stone again later, almost like a birthmark. It is proof that diamonds are not only built by calm growth, but also by strain, pressure shifts, and recovery. Diamonds can show internal graining, like growth rings in wood. Even when a diamond looks perfectly smooth, the inside can reveal subtle texture, a faint banding or directional pattern that appears under certain lighting. This internal graining comes from the way the crystal grew, sometimes with tiny changes in chemistry, sometimes with slight distortions in the lattice as it expanded. It can be so subtle that it feels like the diamond is hiding its handwriting, only showing it when you know how to look. Graining matters because it can influence brilliance and clarity in ways that are not obvious at first glance. It can also affect how the stone responds to cutting and polishing, since different directions can behave differently under the wheel. The most compelling part is what it suggests about time. Graining is a visible trace of change during formation, a reminder that growth was not perfectly uniform and that the environment evolved while the diamond did. It turns a gem into a biography, not just a crystal. You are seeing the diamond's memory of its own becoming, written as lines inside solid carbon. Some diamonds glow under ultraviolet light called fluorescence. In the right conditions, a diamond can surprise you by answering light with light. Under ultraviolet, certain stones emit a visible glow, often blue, sometimes other shades, as if the diamond is briefly revealing a hidden personality. This happens because of specific defects or trace elements in the crystal that absorb ultraviolet energy and remit it at different wavelengths. The effect can be subtle or dramatic, and it can change how a diamond looks in everyday life, especially in sunlight where ultraviolet is present. For some stones, fluorescence can make the diamond appear whiter and brighter, almost like a secret advantage. In rare cases, it can make the stone look slightly hazy, which is why it becomes part of careful evaluation. What makes fluorescence so captivating is that it turns a gemstone into a responsive object, not a passive one. The diamond is not simply reflecting the world. It is converting energy and sending it back in its own voice. Once you have seen a diamond glow, it is hard to believe it is only an ornament. A few diamonds keep glowing after light stops. Phosphorescence. This is where diamonds start to feel almost uncanny. In rare cases, a diamond continues to emit light after the ultraviolet source is removed, holding on to energy and releasing it slowly.
That lingering glow is phosphorescence, and it can last from moments to longer, depending on the stone's internal structure and the nature of its defects. It is not a surface trick. The effect comes from the way electrons get temporarily trapped in the crystal, then return to their normal states over time, releasing light as they do. Some diamonds are known for this behavior in a way that becomes part of their identity, almost like a signature that only appears in darkness. For a viewer, the wonder is immediate. A gemstone that keeps glowing feels like it is refusing to end the scene. It adds a new dimension to what a diamond can be, shifting it from sparkle to afterglow, from reflection to memory. The stone briefly becomes its own light source, then gradually returns to silence, as if it was breathing out the last of a hidden charge. Blue diamonds often owe their color to boron atoms. Blue diamonds are not painted by the sky, they are altered by chemistry. In these stones, tiny amounts of boron can slip into the carbon lattice during growth, changing how the diamond absorbs light and leaving behind a blue hue that can range from soft to strikingly intense. What makes this especially fascinating is that boron does more than tint the gem. It can also change the diamond's electrical behavior, giving some blue diamonds properties that ordinary diamonds do not share. That means the color is not merely visual. It is physical proof that the crystal formed in an environment where boron was available and able to join the structure. The result is a gemstone that carries a trace of its birthplace, like an accent you cannot remove. Blue diamonds have also gathered an outsized cultural reputation, partly because they are rare, and partly because they look like something you would not expect from carbon. When you learn the color comes from a few borrowed atoms, the wonder deepens. A tiny substitution can rewrite the entire identity of a stone. Yellow diamonds usually get their color from nitrogen atoms. Yellow is often the most approachable diamond color, warm and unmistakable. Yet its cause is surprisingly specific. Nitrogen atoms can replace or cluster among carbon atoms in the crystal, altering which wavelengths of light the diamond absorbs. The stone then returns the remaining light with a yellow tone that can be pale, vivid, or even intensely saturated. What makes this compelling is that nitrogen is one of the most common impurities in diamonds, which means yellow can be a kind of natural signature of how the diamond grew. The arrangement matters. Nitrogen scattered one way can create one kind of color, while grouped differently, it can change the shade and intensity. So the diamond's yellow is not just a color. It is a pattern, a structural decision locked within the crystal itself. For the observer, this turns yellow from a simple color into a signal.
The stone is quietly conveying information about how it formed, how it grew, and the chemistry of the deep environment it came from. It is warmth with a history behind it. Light explained at the level of atoms. Pink diamonds can arise from distortion within the crystal lattice rather than from pigment. They seem as though they should be tinted by some hidden dye, yet their color can emerge from stress. In certain stones, the carbon lattice is warped during formation or later deformation, producing subtle shifts in how the crystal bends and reflects light. The result is pink, sometimes soft and delicate, sometimes so strong it feels impossible for a diamond. This is one of the most captivating color stories because it is not about adding an element, it is about bending the structure itself. The diamond becomes pink because it was pushed, shifted, and changed internally. Yet it kept growing or kept surviving. In that sense, the color is a scar that turned into beauty. It also explains why pink diamonds can be so rare and prized. The conditions that create the right distortion without destroying the crystal are not common. For the listener, it reframes the idea of color as biography. The stone is not merely colored. It has been shaped by pressure and strain in a way that permanently changed how it speaks to light. Green diamonds can be colored by natural radiation over time. In some stones, the green is not a dye and not a mineral impurity. It is a change to the diamond's outer crystal caused by radiation from surrounding rocks, often over very long periods. The effect can be so shallow that cutting or polishing removes it, which is why true green can be rare, and why some green diamonds show color concentrated near the surface. When the color survives, it can appear as patches, skins, or delicate zones that hint at where the diamond rested underground after its violent arrival. It is a strange thought that a diamond can be shaped twice, first by deep pressure that formed it, then by invisible energy that touched it later. This makes green diamonds feel like layered histories, a gemstone with a second chapter written after birth. In the best examples, that green becomes proof that the diamond spent quiet time in the earth, absorbing a faint environmental signature, like a stone keeping a memory of its own burial.
Brown diamonds can reflect intense deformation deep underground. Brown diamonds often carry their color like a record of stress rather than a simple tint. Deep inside the earth, a diamond can be squeezed, shifted, and bent at the atomic scale without breaking apart. That internal distortion changes how the crystal absorbs and transmits light, bringing out tones that can look like honey, cognac, or deep chocolate, depending on strength and structure. For a long time, many brown stones were undervalued, partly because people chased icy whiteness, but they are among the most honest storytellers. Their color can be a fingerprint of movement in the deep earth, a reminder that a diamond is not always born in calm conditions. Some brown diamonds also show complex optical effects, with flashes that feel warmer and moodier than a colorless stone. They can make you rethink what beauty means in gems. Instead of pretending the earth was gentle, a brown diamond quietly admits it was pushed hard, changed by pressure, and still emerged intact, carrying that experience as color. Colorless diamonds are not color-free, just balanced to our eyes. A truly perfect absence of color is rarer than most people realize, because almost every diamond has some subtle absorption that nudges it toward a faint tint. What we call colorless is often a diamond whose tiny biases cancel out enough that the eye reads it as clear, especially when it is viewed face up in a setting designed to flatter it. Professional grading is done under controlled lighting and against reference stones, because ordinary environments can hide or exaggerate warmth. Even the metal around a diamond can change what you perceive, with yellow gold lending richness and white metals sharpening the impression of coolness. This makes color feel less like a fixed trait and more like a conversation between crystal and observer. A diamond that looks icy in one room can look slightly creamy in another. Not because it changed, but because your eyes and the light did. The wonder is that colorlessness is often an illusion, achieved by balance, not a total void. And that balance is part of what makes these stones feel so clean and quiet. Some diamonds show a rare effect called color change under lighting. A few diamonds behave like they have two identities, shifting their apparent color when the light source changes. Under daylight or fluorescent light, they may lean one way. Then, under warmer indoor lighting, they can tilt toward a different hue. The reason sits in how the stone absorbs certain parts of the spectrum and how different bulbs feed the diamond different mixes of wavelengths. Your eyes also play a role, because human color perception adapts to its surroundings. So the same stone can feel newly tinted when the room changes. This effect is uncommon, and when it appears naturally, it can make a diamond feel almost alive, as if it is responding rather than simply reflecting. It also creates a quiet kind of suspense. You do not fully know the stone until you have seen it in multiple places. Morning light, evening light, and everything in between. A color change diamond is less like a fixed object and more like a small performance revealed only as the lighting shifts. The term diamond comes from a Greek word meaning unbreakable. The name itself carries a promise. The word diamond traces back to the Greek adamas, a term used for something unconquerable or unbreakable. And it makes sense that people reached for that language when they encountered a stone that resisted their tools. Long before anyone understood crystal lattices or carbon chemistry, hardness was a kind of magic you could feel with your hands. A material that would not scratch, that kept its edge, that seemed to ignore damage. naturally attracted words about permanence and power. The fascinating part is that a name can shape culture. Calling a stone unbreakable nudges it into the role of symbol for loyalty, endurance, and status, even when the physical reality is more nuanced. Language turns an observation into a legend. And once a legend exists, it can travel farther than any gemstone. The name diamond does not just label the mineral. It frames how humans have imagined it for centuries as something that stands against time and refuses to yield.
Ancient Tyre Indians traded diamonds long before Europe understood them. For a long time, the world's best-known diamonds came from India, and people there valued them when much of Europe still had little direct access or context for what the stones were. Diamonds moved through trade networks as rare portable wealth, traveling with merchants and changing hands in courts, where gemstones were part of diplomacy and status. In early uses, diamonds were not always cut for sparkle the way we expect today. They could be treasured as natural crystals, admired for hardness, rarity, and the strange way they caught light, even without modern faceting. India's role also shaped early stories about diamonds, mixing practical trade with mythic ideas about protection and power. What makes this captivating is the sense of time travel. The diamond in a modern ring is part of a much older human habit. The urge to carry a piece of earth that feels special and to let it speak for you.
Long before global branding, diamonds were already global objects, moving by human desire and human roots across continents. Brazil once overtook India as a major diamond source. When diamonds were discovered in Brazil, the map of the diamond world shifted. Supply routes changed, fortunes moved, and the idea of where diamonds came from expanded beyond the older assumption that India was the central source. Brazil's deposits included stones found in river gravels and other secondary environments, which helped fuel rushes where people searched sediments instead of tunneling into bedrock. That change mattered because it altered how diamond hunting looked and felt. It became tied to landscapes of rivers and valleys, to labor and speculation, to the belief that wealth might be waiting in the next pen of gravel. The broader impact was cultural too. As new sources emerged, diamonds became less mysterious as a concept and more integrated into global trade, with growing systems for sorting, selling, and moving stones across oceans. Brazil's rise is a reminder that diamonds are not only geological, they are historical, reshaping economies and expectations the moment a new region proves it can produce them. A single discovery can relocate an entire industry's attention. South Africa's discoveries reshaped the global diamond industry. When major diamond finds erupted into public awareness in South Africa, the scale of diamond production and the structure of the business transformed. Mining shifted toward large operations built around kimberlite pipes, and diamonds became something that could be extracted in enormous volumes compared to many earlier sources. That abundance created a new challenge. If diamonds became too common, their aura of rarity could weaken. The industry responded by building modern systems of distribution, sorting, and long-term control of supply, alongside powerful messaging that linked diamonds to life milestones. This is where diamond history becomes both industrial and psychological. The stones were still rare in an individual sense, but the flow of them into the market became managed, shaped by logistics, finance, and carefully constructed meaning. South Africa's role is also a reminder that a diamond rush is not just people digging. It is infrastructure, labor, power, and the creation of entire towns and networks around a single resource. Diamonds did not only change jewelry, they changed how a global commodity could be organized around desire scarcity, and story. Botswana's diamond wealth transformed its modern economy. Botswana is often mentioned because diamonds became a major pillar of national revenue and helped fund development in ways that stand out in the region. Instead of the resource simply vanishing into private hands, diamond income has been tied to public spending and long-term planning, including investments in health, education, and infrastructure. The result is not a fairy tale with no problems, but it is widely seen as a case where governance choices shaped how resource wealth affected a country. That is what makes the story so compelling for a viewer. A gemstone can be more than personal luxury. It can become a lever for national change depending on policies, partnerships, and how money is managed over decades. Botswana's diamonds also complicate the way people talk about mining, because the impact is not one single narrative. It can include hard realities and ethical questions, and also genuine economic transformation. The diamond becomes a reminder that resources are not destiny. The outcomes depend on human decisions, and those decisions can echo through generations.
Canada produces diamonds from far northern mines in ancient rock. Canada's diamond story feels different because of geography. Many Canadian diamonds come from remote northern regions where mining happens in landscapes defined by cold, distant, and short construction seasons. The diamonds are hosted in very old crust rocks, and the mines operate with heavy logistics, moving supplies across ice roads or by air, planning around weather that can turn simple tasks into major power operations. This setting changes the public image of diamonds. Instead of tropical rivers or desert mines, the backdrop can be tundra and boreal forest, with strict environmental planning and close attention to wildlife and water. Canadian diamonds also helped popularize modern tracking and certification programs, partly because the supply chain was easier to document from a smaller number of operations. For many buyers, Canada introduced a new kind of diamond origin story, one tied to cold landscapes and a sense of regulated transparency. It is fascinating to realize that the same crystal that formed deep underground can surface in places that feel almost otherworldly in their alertness, then travel to city jewelry counters thousands of miles away. Ethical sourcing efforts track diamonds from mine to market. Because diamonds are small, valuable, and easy to move, their supply chains can be complicated. And that complexity is exactly what ethical sourcing tries to reduce. Tracking efforts can include sealed parcels, documented transfers, audits, and chain of custody paperwork designed to keep stones linked to their origin as they travel through cutting, trading, and retail. Some systems also rely on inscriptions, digital records, and independent verification to strengthen confidence. The goal is not perfect purity of history, which is hard in any global commodity, but improved transparency, so buyers can make informed choices. What makes this interesting is how modern the diamond world has become. The romance of a gemstone now lives alongside compliance, traceability, and data, because consumers and regulators have demanded clearer answers about labor conditions and conflict financing. Ethical sourcing is also a reminder that diamonds are not only geology, they are human networks. If you want a diamond to carry a story you feel good about, the story has to be documented, not assumed. Tracking turns a stone into a traceable object with a paper trail, and that paper trail becomes part of its value. Lab-grown diamonds can reduce mining impacts, but energy choices still matter. Lab-grown diamonds can avoid some impacts associated with mining, such as large-scale excavation and the disturbances that come with it. But the environmental story does not automatically become simple, because growing diamonds requires energy,
and the climate impact depends heavily on how that electricity is generated. A lab powered by the carbon grids or renewables can have a very different footprint than one powered by fossil-heavy electricity. There are also other inputs, like equipment, gases, and the broader manufacturing supply chain, which means responsible production is about more than the crystal itself. This is what makes the topic worth exploring. It is not a clean binary of good versus bad. It is a set of trade-offs that depend on location, oversight, and transparency. For viewers, the hook is that diamonds have entered the world of modern sustainability debates, where origin is not only romantic, it is measurable. The choice becomes less about what looks real and more about what impact you want to support. In that sense, lab-grown diamonds are not just a product, they are a new chapter in how humans decide what value should mean. Every diamond is a pressure-borne record of Earth's deep interior. A diamond is one of the few objects you can hold that formed in a realm where the planet is still actively reshaping itself. It began as carbon subjected to intense pressure, arranged into a crystal that can preserve clues about its environment far better than most rocks do. Even when a diamond appears simple, it carries quiet information in its growth features, its trace chemistry, and the minute stresses locked into its structure. That makes it more than an object of beauty. It is a durable messenger from depth, a physical sample of the conditions that shape continents and volcanism, yet remain beyond the reach of our bodies. What deepens the wonder is the contrast between scale and intimacy. Earth's interior is immense, hot, and slow-moving, while a diamond can rest on a fingertip. And yet, that fingertip is holding something formed by the very forces that drive the planet's long rhythms. When you see diamonds this way, the fascination widens. The sparkle becomes secondary. The real wonder is that the Earth managed to send you a record of its hidden world, and you can carry it quietly through an ordinary day. Diamonds also have strong dispersion, splitting light into colors. Dispersion is why diamonds can show those little flashes of red, green, and blue that feel like tiny surprises. It happens because different wavelengths of light bend by different amounts inside the crystal. So white light can separate into colors as it travels and reflects. Not every diamond shows the same amount of this fire because the cut influences how and where the colored rays exit the stone. A design with certain crown heights and facet arrangements can emphasize dispersion, while other choices favor brightness and contrast instead. This creates a fascinating trade. A diamond can be optimized for white brilliance, or it can be tuned to show more colored fire. And the best balance depends on taste and lighting. Some people want a stone that looks bright in every situation. Others chase those colorful flashes that appear like brief signals. Dispersion also helps explain why diamonds can look different under different bulbs, since the spectrum of the light source changes what colors are available to split. The wonder is that a diamond can act like a tiny prism without ever looking like a prism, hiding that physics inside beauty. A diamond's cut creates brilliance, not the diamond itself. Two diamonds can come from similar rough and still feel like different worlds once they are shaped. The cut decides how light enters, where it travels, and whether it returns to your eye as bright flashes or leaks away unseen. This is why gem professionals talk about proportion, angles, and light performance as if they are personality traits. A cutter is making choices that trade weight for beauty, deciding whether to keep a stone heavier or make it livelier. A well-planned cut can make a smaller diamond look more radiant than a larger one with poor geometry, because the eye responds to brightness and contrast more than mass. This is also where human skill becomes part of nature's story. The earth provides the crystal, but the cut decides how it speaks in light. When you see a diamond that looks awake, it is not only because it formed deep underground, it is because someone shaped it with an understanding of optics, symmetry, and restraint, turning raw potential into visible energy. Poor cutting can make an amazing diamond look sleepy. A diamond can be high quality in every way and still look dull if the cut wastes light. When proportions are off, the stone can develop problems with famous nicknames. A window is an area that looks transparent instead of bright, as if you can see through the diamond rather than into it. A nailhead is a dark center that robs the stone of sparkle. A fisheye can create a washed ring that makes the diamond feel flat. None of these flaws require a bad diamond. They come from geometry. This is why cut is often the most unforgiving factor, because you cannot polish your way out of it later. Once the shape is set, the light performance is largely locked in. The most dramatic part is that many casual viewers do not know what they are seeing. They simply feel the lack of life. Their eyes drift away without understanding why. A beautifully cut diamond holds attention because it creates crisp contrast and bright return that the brain reads as energy. Poor cutting does the opposite, even when the material deserves better. The round, brilliant cut was designed to maximize light return. The round brilliant is not just popular, it is engineered. Its shape allows many facets to work together. So light is gathered, redirected, and returned in a pattern that feels bright from multiple angles. That design did not appear by accident. It was refined over time as cutters and researchers experimented with proportions, looking for a balance between brightness, flashes, and rainbow fire. The round outline also has practical advantages because it is efficient to rotate during polishing, and it distributes stress in a way that suits daily wear. But its real power is visual reliability. In many lighting environments, from daylight to a single lamp, a good round brilliant still performs, which is why it became the default image in people's minds when they think of a diamond. It is a cat that tries to be consistently impressive rather than occasionally perfect. When someone says diamond sparkle, they're often picturing this design: a circular arrangement of facets built to catch light quickly and return it with strong contrast.
It is the result of generations of craft turning into a kind of standard language for brilliance. Step cuts straight sparkle for calm, mirror-like flashes. A step-cut diamond does not try to glitter constantly. Instead, it creates broad, clean reflections that slide across the stone like quiet panels of light. Emerald cuts and astra cuts are famous examples, built with long, straight facets arranged in steps. The effect can feel architectural, almost like looking into a deep hallway lined with mirrors. This makes step cuts unforgiving in a different way. They do not hide internal features easily, so clarity becomes more visible, and the cutter's precision is exposed in every line. A tiny mismatch can break the rhythm. When a step cut is done well, it feels poised and intentional, with flashes that come less often but arrive with authority. It can be the difference between a stone that chats constantly and a stone that speaks only when it has something to say. For many people, that calm is the appeal. It is a diamond style that invites you to stare, not because it overwhelms you with sparkle, but because it offers depth, symmetry,
and a slower kind of beauty that keeps unfolding. Diamonds have a very high refractive index, boosting sparkle. Refractive index is the measure of how strongly a material bends light, and diamond bends it dramatically. When light crosses from air into diamond, it slows and changes direction more than it would in many other transparent materials. That bending is part of why diamonds can look bright even when they are small. It also sets up the conditions for light to reflect internally instead of escaping through the sides, especially when the stone is cut within certain angle ranges. This is the hidden reason diamonds can look lively under everyday lighting, not just under spotlights. The stone is doing optical work before any sparkle is even considered. It is guiding photons, redirecting them, and making the interior feel active. What makes this so fascinating is that the effect is not about decoration. It is an intrinsic property of the crystal, a built-in interaction between carbon and light. The diamond is not trying to shine. Its physical makeup forces light to behave differently the moment it enters. That bending, multiplied by many facets, becomes the bright presence people notice across a room. A diamond's polish can be excellent, yet its symmetry can fail. Polish is about how smooth each facet surface is, while symmetry is about whether the facets are aligned and shaped in a coherent pattern. A diamond can have a glassy, flawless polish and still look off if the facet geometry is uneven. The table might be slightly skewed, the cullet might sit off-center, or the crown facets might not meet in a crisp, repeating rhythm. These differences can be subtle, but the eye often senses them as a lack of crispness in the pattern of light and dark. Symmetry is what makes a diamond sparkle look organized rather than messy. It is also why certain stones produce sharp, pleasing patterns when viewed face up. Sometimes described as optical precision, polish supports that by reducing tiny surface marks that scatter light, but it cannot correct a design problem. The fascinating part is that this is where beauty becomes almost musical. The stone is not only bright, it is structured with repeating beats of reflection. When symmetry is strong, the diamond feels intentional, like it has a clean internal logic. When symmetry fails, even a smooth surface can feel confused, and the light does not sing the same way. Diamonds can conduct heat extremely well, unlike many lookalikes. That single trait makes diamond feel less like jewelry and more like an escape artist for energy. Touch a diamond set into metal, and it can steal warmth so efficiently that it seems to run cooler than its surroundings. The reason sits in the crystal's orderly structure, which lets vibrations travel through it with remarkable speed, carrying heat away before it can linger. This is why diamond has found a second life, far from necklaces, in places where overheating ruins performance. Engineers use diamond as a heat spreader in demanding electronics, not because it looks beautiful, but because it behaves like a thermal superhighway. It is also why a diamond can feel almost startling against the skin in a cold room. Even when it has been indoors all day, you are not sensing coldness created by the stone. You are sensing how quickly it pulls heat from you and shares it with everything around it, as if the diamond is refusing to keep warmth for itself. That heat conductivity helps gem testers separate diamond from glass. In a shop, the most convincing fakes often win by looking right, not by behaving right. A tester takes advantage of that, using a small probe that delivers a controlled bit of heat and watches how fast the stone moves that heat away. Diamond clears it quickly, while many common simulants hold onto it longer, like a slow reply to a simple question. What makes this fascinating is how the test exposes the difference between appearance and identity. Glass can shine.
cubic zirconia can sparkle. Even carefully crafted materials can mimic the look under bright lights. But when the instrument asks the stone to move heat, the imitation often hesitates. It is a quiet moment of truth, based on physics rather than romance. Good testing also involves care, because some materials can fool simple devices, and skilled gemologists use multiple checks to avoid mistakes. Still, the core idea feels almost poetic. A diamond reveals itself by how it handles energy, not by how it looks.
It proves that beauty is only one part of what the crystal is.
Diamonds are electrical insulators, except some colored types. Most diamonds do not let electric current pass through them in any ordinary way, which is surprising for something that feels so powerful and sharp. The crystal lattice holds electrons tightly, leaving little room for the easy flow that makes a metal conductive. That insulating behavior is one reason diamond has been used as a protective material in certain high-performance contexts where you want strength and stability without unwanted current. But the real intrigue comes from the exception. In rare cases, specific impurities or defects change the rules, nudging diamond towards semiconducting behavior. That means a gemstone can sit on a boundary, usually refusing electricity, yet capable of switching roles when its internal chemistry is altered in just the right way. It is not magic, it is structure.
A tiny change in the crystal can rewrite how charge moves, turning a classic insulator into something closer to an electronic material. It also reshapes the idea of diamonds as purely decorative. Some are quiet guardians against current. Others become participants in it, depending on what the crystal allowed inside while it grew. Blue boron diamonds can conduct electricity like a semiconductor. Boron is a small intruder with a big influence. When it slips into the diamond lattice, it can create pathways for charge carriers, giving certain blue diamonds an electrical personality that most diamonds never have. That is part of why these stones fascinate scientists as much as collectors. They are gems with an extra layer of behavior hidden beneath the color. Semiconductor-like conduction means the diamond is not simply on or off.
Under the right conditions, it can carry current in a controlled way, which opens doors for specialized electronics designed to handle high power and high heat. It is also a reminder that color in diamonds can be more than a visual flourish. The blue is a clue that something fundamental changed in the crystal's makeup. A few foreign atoms did not just tint the stone, they altered its relationship with energy and charge. This makes a blue boron diamond feel like a hybrid, part gemstone, part device, born deep underground and yet speaking a language engineers understand. Diamond is transparent, yet it can be grown as black. Black diamond can feel like a contradiction, and that is exactly why it is so compelling. Darkness in a diamond often comes from how light is blocked, scattered, or absorbed inside the stone, rather than from a simple coat of color.
In some cases, it is an intense concentration of inclusions and internal features that break up light until almost none returns clearly. In others, it can involve a dense network of tiny crystals or defects that turn transparency into opacity. The result is a gem that does not try to dazzle with bright flashes. It offers depth, a kind of quiet gravity. Cutters approach it differently too, because the goal is not to showcase internal clarity, but to shape surface reflections and silhouette, letting the stone read as sleek and deliberate.
black diamond also changes the emotional meaning people attach to the material. It moves from celebration toward mystery, from bright signal to dark statement. And it proves something important. Diamond is not one look. It is a whole family of behaviors, and transparency is only the version we are most used to praising. Carbonado diamonds are rugged, dark, and often polycrystalline. Carbonado stands out as one of the most unusual diamond forms because it is rarely a single transparent crystal. Instead, it is commonly a compact mass of countless tiny diamond grains bonded together, producing a texture that can appear porous and uneven when compared with gem-quality diamonds. This internal makeup can make carbonado exceptionally tough in a practical sense, resisting fracture in ways that differ from typical single crystal stones. Rather than one large lattice with clean cleavage planes, it behaves more like a collective. Stress is dispersed across innumerable boundaries, making it far more difficult for a crack to travel cleanly through the material. Carbonado's deep black appearance and rough texture once made it feel less glamorous. But its story is fascinating. It does not fit the simple fairy tale of a perfect crystal. It feels more like a geological artifact, a material shaped by unusual conditions and then delivered to the surface as something already hardened by complexity. Historically, it has also been useful in industry because toughness and abrasion resistance matter more than sparkle. Carbonado invites a different kind of ore. It is diamond that chose resilience over tarity. Some black diamonds contain many tiny crystals fused together. Imagine building a gemstone from countless miniature diamonds pressed into one body, each with its own orientation, then locked into a single dark mass. That is the idea behind many black diamonds that show a granular polycrystalline nature. Under magnification, the surface and interior can reveal a mosaic of microscopic grains. And that graininess is part of what swallows light. Instead of letting light travel cleanly through, the stone repeatedly interrupts it, scattering and absorbing until brightness disappears. This internal patchwork can also change how the stone behaves during cutting and polishing. The cutter is not dealing with one uniform crystal. They are shaping a composite where tiny boundaries can influence how the material responds. That can make the finished look feel different too, more like a sleek stone than a window of brilliance. What makes this captivating is that it reframes the idea of a diamond as singular. A black polycrystalline diamond is a crowd-aid solid, a gemstone built from many, carrying a complexity that you can sense even when it looks like pure darkness. Diamond can be made in laboratories using high-pressure methods. There is a way to recreate the deep earth in a controlled box. High-pressure, high-temperature growth compresses carbon and heats it until diamond becomes the favored form, then uses a small diamond seed as a template for new crystal to build upon. It is not instant, and it is not fake. It is a human-made route to the same atomic structure that nature forms underground. What makes this so? A chamber is filled with carbonary gases, energized, so carbon atoms break free and settle onto a diamond seed. Over time, the crystal expands one layer at a time, building a diamond with remarkable control over shape and purity. This method is fascinating because it behaves like a slow construction project rather than a sudden transformation. You can tune growth conditions, adjust the environment, and aim for material suited to different purposes, from gemstones to specialized technological components. It also changes the story of diamond from deep earth relic to engineered material. In some cases, CVD diamonds can be made with fewer inclusions and with properties tailored to electronics, optics, or cutting applications. But it is not simply about perfection. It is about intention. CVD shows that diamond is not only something found, it is something cultivated. That idea can feel quietly mind-bending. A crystal famous for being born under crushing pressure can also be assembled patiently, atom by atom, in a chamber built by people. LeBrown diamonds can be chemically identical to mined diamonds. This is where the conversation becomes wonderfully subtle. If you compare the basic chemistry and crystal structure, a lab-grown diamond can match a mined diamond because both are carbon-rayed in the same diamond lattice. That means the difference is not a simple matter of real versus not real. It is a matter of origin and the small clues each root leaves behind. Natural diamonds often carry geological signatures tied to their formation environment, while lab diamonds may show growth patterns or trace elements that reflect manufacturing conditions. That is why gemological laboratories use sophisticated methods to identify origin. Not because the material is different in a simple way, but because the history is different. For viewers, this is a powerful shift. Diamond becomes less of a singular category and more of a story you can trace. One stone formed through Earth's deep processes and violent delivery. Another was grown by controlled human technique. They can share the same chemistry, yet belong to different narratives, ethics, and markets. The wonder is that atoms do not care about romance. They care about conditions. And humans now control some of those conditions well enough to make a diamond that nature would recognize as its own. Metal diamonds can show nitrogen patterns that reveal their history. Nitrogen does not always sit inside a diamond in the same way. Over long stretches of time, those nitrogen atoms can move and regroup within the crystal, shifting from single atoms to pairs and larger clusters. That rearrangement acts like a slow internal clock because it depends on heat exposure and time spent at depth. When gemologists analyze how nitrogen is arranged, they are not just measuring impurity, they are reading the diamond's thermal past, like finding out whether it lived in a warmer pocket of mantle or a cooler one, and for how long. It is a rare moment where a gemstone behaves like an archive rather than a treasure. Two diamonds can look similar from the outside, yet their nitrogen patterns can quietly announce that their life stories were nothing alike. One may have rested deep and warm for ages, allowing nitrogen to cluster. Another may have had a different journey, locking in an earlier stage. The diamond carries a history you cannot see, but you can learn to interpret. Isotopes in diamonds can hint at where the carbon came from. Not all carbon is the same, even when it becomes diamond. Carbon atoms come in slightly different versions, called isotopes, and the ratio between them can shift depending on the source. Some carbon signatures suggest a deep mantle origin, while others look more like carbon that once cycled through surface environments. When scientists measure these isotopic fingerprints, they can infer whether the diamond's carbon likely came from primordial mantle material or from carbon that traveled through oceans, sediments, and living systems before being dragged downward. It turns a gem into a kind of biography of an atom. The diamond is not only telling you how it was shaped, it is hinting at where its building blocks once lived. This idea can feel almost dizzying. A stone in a jewelry box might contain carbon with a story that began in deep earth chemistry, or carbon that once moved through a much shallower world, then took a one-way trip into darkness.
Isotopes do not give a single, simple answer every time, but they open a door to origins that go beyond sparkle. Some diamonds may form from carbon carried down by subduction. Subduction is Earth's slow swallowing motion, where oceanic plates slide beneath continents and descend into hotter, deeper regions.
Along with rock, that process can carry carbon in many forms, including carbonates in altered crust and carbon-rich sediments that began as seafloor deposits. As that material moves downward, pressure and heat change its chemistry, releasing carbon-bearing fluids that can infiltrate mantle rocks. In certain conditions, that carbon can crystallize as diamond. What makes this so gripping is the loop it suggests. Carbon that once moved through surface cycles can be pushed into the deep, transformed, and returned later as a gemstone that looks like it came from nowhere. It is not a quick journey. It is a planetary relay race that can span immense time. This also reframes diamonds as part of Earth's carbon system, not separate from it. A diamond can be the end product of tectonic recycling, where the planet takes surface carbon, sends it down, and reshapes it into something stable enough to survive a violent ride back up. A few diamonds come from extreme depths, called super deep diamonds. Most diamonds already feel impossibly deep, but a small subset pushes that idea further. Super deep diamonds form far below the typical diamond zone, and the proof often comes from what they carry inside: minerals that only stabilize at extraordinary pressures. These stones are like postcards from layers of Earth that are otherwise known mostly through seismic waves and indirect models. The wonder here is not just depth, it is access. Humans cannot drill anywhere near those regions, yet a super deep diamond can deliver a physical sample from that hidden world into our hands. It can also show that carbon moves through the planet in ways that reach much farther down than many people imagine. The diamond becomes evident that deep Earth is chemically active with fluids and reactions capable of building crystals under conditions that would crush ordinary materials. Super deep diamonds are rare, and that rarity makes them feel like exceptional messengers. They do not simply sparkle. They testify that Earth's interior has layers of complexity that can still surprise us, and that sometimes the planet accidentally sends us a piece of its most remote realm. Super deep diamonds can form in the transition zone inside Earth. The transition zone sits between the upper and lower mantle, and it is famous among geoscientists because minerals change structure there under pressure like matter switching outfits. It is also a region that may store significant amounts of water locked inside certain mineral forms, which can influence how rock flows and how the mantle circulates. When diamonds form in this zone, they become rare carriers of information from a place defined by transformation. Their inclusions can point to the pressure conditions of that layer, and they can hint at what kinds of fluids were present when the diamond grew.
The fascinating part is that this zone acts like a boundary world. Not surface, and not deep mantle in the usual sense, but a middle region where the rules shift. A diamond born there is a product of that shift. A crystal formed where Earth is actively reorganizing itself at the atomic level. Holding such a stone means holding evidence that the planet's interior is not uniform. It has thresholds, and those thresholds can create objects that survive long enough to reach daylight. Some super deep diamonds might form even deeper in the lower mantle. The lower mantle is vast, making up a huge portion of Earth's volume, and it is a place we understand mostly through vibrations, experiments, and careful inference. If diamonds form there, they represent an even rarer bridge between knowledge and touch. The conditions are intense,
with pressures so high that mineral structures differ from those near the surface, and temperatures that demand extraordinary stability from any crystal. Evidence for lower mantle origins often comes from inclusions consistent with minerals expected at those depths, preserved by the diamond's protective grip. The emotional punch is that these diamonds would be travelers from a region that shapes the entire planet dynamics, including how heat escapes and how mantle convection drives plate tectonics over long timescales. A lower mantle diamond is not just deep, it is from the engine room's deeper section. It suggests that carbon can crystallize into diamond under conditions that seem almost beyond imagination, then remain intact through ascent and erosion. If confirmed, each one is a physical handshake with a part of Earth no human will ever visit, yet which quietly influences everything we build on the surface. Diamond stability depends on pressure, not just temperature. People often assume heat is the deciding factor, but for diamond, pressure is the true gatekeeper. At sufficiently high pressures, the diamond arrangement of carbon becomes favored, meaning it is the stable form that carbon wants to be. Temperature still matters, but without the right pressure, diamond is living on borrowed time. This is why diamonds form deep and why the journey upward is so dramatic. As pressure drops, the stable identity of carbon shifts, and diamond is no longer the form nature prefers. Yet diamonds do not instantly change the moment conditions change. They can endure as a metastable material, like a flawlessly built structure standing in a climate it was never meant for, simply because change unfolds slowly. This perspective gives diamonds a different kind of awe. They are not only born from extreme conditions, they are maintained by a kind of stubborn delay. The stone you see in a ring is a survivor of a shift in stability. It is a crystal shaped by the rules of a deep, high-pressure world, still present within our low-pressure one. Nature's transformations are not always quick. Near Earth's surface, graphite is the stable form of carbon. In the environment we inhabit, carbon generally favors the softer arrangement known as graphite, where atoms are stacked in sheets that slide easily past one another. That is why pencils work and why graphite feels so familiar. It is also why diamonds are such an odd guest at the surface. They are not the form carbon typically chooses here, even though they can persist for a very long time. This contrast makes diamonds feel like visitors from a deeper set of raws. Graphite is stable at low pressures, which means if carbon were free to decide from scratch near the surface, it would not usually choose diamond. But once diamond exists, it can remain as a kind of holdover, a crystal trapped in its own structure. This also explains why diamonds can be altered by certain processes that encourage carbon to rearrange, especially under high heat. The key fascination is the identity shift. Carbon has multiple personalities, and the surface environment encourages one of them. Diamonds are the rare case where a deep earth personality keeps showing up in a place where it is not the favored form. Like a stubborn accent that refuses to fade, diamonds survive at the surface because transformation is very slow. If diamond is not the stable choice near the surface, why do we still have natural diamonds at all? The answer is patience, but not the human kind. Converting diamond into graphite requires atoms to break and reattach in a new pattern, and that rearrangement is sluggish under ordinary conditions. The diamond lattice is rigid, And without the right combination of heat catalysts or time at elevated temperatures, the transformation crawls. So diamonds can sit in river gravels, in rock, or in jewelry for ages without changing, even though the surface environment technically favors a different carbon structure. This creates a beautiful tension. A diamond at the surface is not the end of a story. It is a paused chemical possibility. It is stable in practice because the pathway to change is difficult, not because the surface is its natural home. That makes each diamond feel like a preserved exception. It is a deep earth crystal living in a shallow earth setting, surviving because nature's rearrangements often happen on timescales that do not match our attention. A diamond can cleave along planes despite its famous toughness. Hardness makes diamonds resistant to scratching, but cleavage is about how a crystal can split when force strikes in the wrong direction. Diamonds have specific planes in their lattice where bonds align in a way that can allow a clean break. This is why cutters plan so carefully. A diamond can resist abrasion for a lifetime, yet a sharp impact at an unlucky angle can cause it to chip or split. The drama is that the same orderly structure that gives diamond its strength also gives it directions of vulnerability. Skilled cutting historically relied on understanding this hidden map inside the stone, using controlled force to separate rough into workable pieces. Then shaping with precision rather than brute strength for everyday wear. This is why settings matter, why exposed corners can be risky, and why certain shapes require thoughtful protection. The fascination is not that diamonds are fragile. They are not. It is that they are structured, and structure always comes with rules. A diamond is not an indestructible blob. It is a crystal with geometry, and geometry has preferred ways to behave when stressed. Cleavage makes diamonds risky to cut if struck the wrong way. A cutter does not fear the diamond's hardness. They respect its directions. Inside the crystal are planes where the atomic structure can separate cleanly if a force lands just right. In the workshop, that means one careless strike can undo months of planning in a single instant. Traditional cleaving was once done with a deliberate groove and a precise tap. A controlled gamble that could split a rough stone neatly or ruin it completely. Even with modern tools, the danger has not vanished. It has simply changed shape. Pressure, vibration, and tiny stresses can travel through the stone in unexpected paths, and a hidden weakness can open where no one intended. This is why so much of diamond cutting is mental before it is physical. The cutter studies the rough, imagines the internal map, and chooses the safest path to beauty. It is a quiet reminder that a diamond is not just tough, it is organized, and organization comes with rules that must be obeyed. Diamond hardness resists scratching, but it does not guarantee strength. Hardness is about one kind of battle, the fight against being scratched. Strength is a different story, the ability to survive impacts, pressure points, and sudden shocks without cracking. A diamond is extraordinary at resisting abrasion, yet it can chip if struck on a vulnerable edge, especially in shapes with sharp corners or exposed tips. This surprises people because we talk about diamonds as if they are invincible, when in reality, they are more like finely made glass with a fortress surface. Their stiffness can make them less forgiving under certain blows because the energy does not dissipate easily. It concentrates. That is why jewelers care about how a diamond is set, how high it sits, and what parts are protected by metal. It is also why someone can wear a diamond daily for years with no scratches, then damage it in one unlucky moment against a countertop or a doorframe. The wonder is that nature built a material that wins the slow war of wear, while still asking us to treat it carefully in the sudden moments. The toughest diamond shape is not always the prettiest.
Some cuts are designed to handle real life, not just showroom lights. A round shape has no corners to catch on things, and its curves help spread force, which can make it more forgiving during everyday wear. Meanwhile, shapes with sharp points like marquise or pear can be visually dramatic but physically exposed, because a tip concentrates stress in a small area. Even a stunning princess cut, beloved for its crisp geometry, has corners that often need protective prongs. This creates a fascinating tension between aesthetics and engineering. The most glamorous silhouette can also be the most demanding, asking for careful setting choices and mindful wear. And the most durable outline can sometimes feel less bold to someone chasing a particular look. Choosing a shape becomes a quiet act of design philosophy. Do you want elegance that challenges the world, or elegance that blends into it and lasts? Diamonds make you answer that question with geometry, not words. Some inclusions create unique patterns collectors actually love. Not all collectors chase emptiness. Some chase signature. In certain diamonds, inclusions arrange themselves into patterns that feel like private artwork. Tiny constellations of pinpoints, delicate veils, or neat-like crystals that catch light in surprising ways. These stones can feel more personal because their interiors are unmistakable, like a face you would recognize again. Certain named effects have become collectible, such as diamonds that show a star-like reflection from aligned inclusions when cut in specific ways. In other cases, the appeal is simply rarity of character, a feature that makes the stone different from the clean, standardized look most people expect. This kind of collecting treats a diamond less like a status object and more like a specimen with personality. It also makes the diamond feel more connected to its origin, because inclusions are evidence of growth conditions, not flaws added later. When a collector chooses such a stone, they are choosing story over perfection. The diamond becomes a conversation piece, not because it is flawless, but because it is distinctive in a way no other stone can copy. Fancy color diamonds are valued for strong, natural color. A fancy color diamond is prized when its color is not faint, not apologetic, but confidently present. The grading focuses on hue, tone, and saturation, describing how pure the color feels, how light or dark it appears, and how intense it is. What makes these diamonds so fascinating is that they shift the goal entirely. In a colorless diamond, people often chase the absence of tint. In a fancy color, the color is the treasure, and the cut is chosen to show it, sometimes even at the expense of some brightness. The setting choices change too, because surrounding metal can amplify or contrast the hue. Natural fancy colors also carry the excitement of scarcity, because the conditions that create strong color are uncommon, and the distribution of that color within a stone can be uneven or zoned in ways that make cutting cow a puzzle. A fine, fancy-colored diamond feels like nature leaning into expression rather than restraint. It is not trying to be pure glass. It is trying to be unmistakable. Blue, pink, and red diamonds can be extraordinarily rare. Some colors are rare because the needed conditions are rare, and that rarity can make certain diamonds feel almost mythical. Blue and pink can already be scarce in natural form, and true red is among the most elusive colors in the diamond world. The market reflects this with intense collector interest, museum-level attention, and records that can surprise even people who know gemstones well.
What makes the rarity feel different from ordinary scarcity is that it is not about one mine or one region alone. It is about the unlikely alignment of formation, history, chemistry, and survival through transport and cutting. Even when a diamond has the right color, keeping that color vivid after shaping is its own challenge, because cutting can change how the color presents to the eye. This is why famous colored diamonds become characters in their own right, passed through history with names and reputations. A rare color diamond is not just a pretty object, it is a statistical anomaly that survived the Earth, survived discovery, and then survived the human decision to cut it. That chain of improbability is part of the thrill. The Hope diamond is famous for its deep blue color. Its reputation begins with a stone once known as the French blue, cut from an earlier diamond that traveled from India into the courts of Europe.
Over time, it passed through royal hands, political upheaval, private collections, and finally into public view, where it became one of the most recognized gems on Earth. What makes it so captivating is that it does not rely on size alone. Its color is the headline, a saturated blue that feels almost impossible for a diamond, paired with a history that keeps reappearing in books, museum halls, and late-night conversations. Stories have gathered around it the way dust gathers on old velvet, including dramatic rumors that museums work hard to separate from documented facts. Today, it sits as an object you can stand near, looking at the same stone that once moved through palaces, not as a symbol of mystery, but as a reminder that real history can be stranger than myth. The Cullinan diamond produced several major stones in the British crown jewels. It began as an enormous rough crystal discovered in South Africa, a find so large that it instantly became a problem as much as a treasure. A stone that size is not simply cut, it is negotiated with, because one wrong decision can waste what cannot be replaced. The solution was bold. Expert cutters studied the rough for weaknesses and possibilities, then split it into many pieces, turning one discovery into a family of important diamonds. Several of these gained fame in their own right, set into regalia and worn during moments meant to signal continuity and authority. What is intriguing is that the public often imagines one single legendary diamond, when the reality is multiplication. One original stone became many symbols, each with its own form, setting, and purpose. It is also a story of craftsmanship under pressure. The largest rough diamond ever discovered at the time was not transformed into one flawless jewel. Instead, it became a chain of decisions, each one engraving history into carbon. The Koh-i-Noor carries a long and contested journey across empires. Its story is less about geology and more about how humans use objects that embody power and status. Over centuries, it moved through powerful courts in South Asia and Central Asia, tied to changing rulers, shifting borders, and the rise and fall of empires. Different traditions name different chapters as the most important, and that disagreement is part of why the diamond remains so charged. Today, it is associated with the British crown jewels, and its presence there continues to prompt debate and diplomatic conversations about heritage and rightful ownership. What makes this diamond feel unique is that it is not only admired,
It is argued over, as if the stone has become a physical placeholder for history itself. Even its cutting history reflects changing tastes, with reshaping done to match the aesthetic expectations of a new era. The Kaor reminds you that diamonds are not born political, but they can become political when societies attach meaning to them. It is a gemstone that carries not just light, but legacy. The Regent diamond once belonged to French royalty. Its path into legend began with discovery in India and a journey into European hands where it was cut and named, then pulled into the gravitational field of French power. For a time, it became part of the visual language of monarchy, set into crowns and ceremonial objects where gems were used like punctuation marks in a sentence about authority. Then history turned, and the diamond had to survive the same turbulence that toppled the people who once claimed it. That survival is part of its quiet drama. Many royal objects are lost to time, melted down, stolen, or scattered. The Regent endured, moving through new owners and new political realities, eventually becoming a museum piece rather than a private symbol. Seeing it in that setting changes the feeling. It becomes less like a possession and more like evidence, a physical artifact that outlasted the system that elevated it. The Regent diamond is fascinating because it shows how a gemstone can move from personal luxury to national story without changing its material at all. The Tiffany yellow diamond is one of the largest yellow gems ever cut. Unlike diamonds prized for icy whiteness, this one was chosen for its color, a rich yellow that reads as deliberate rather than accidental. Its size makes it notable, but the real achievement is the way it was cut to emphasize that hue, giving the stone a presence that feels warm and unmistakable even without perfect lighting. Over the years, it became closely tied to a brand identity, appearing in exhibitions and special events as a kind of ambassador for what fancy color diamonds can be. It is not a diamond most people will ever see in person, yet it has a public life that many gemstones never achieve. That public life is part of the fascination. A diamond can be locked away, or it can be displayed as cultural theater, a symbol that represents taste, craftsmanship, and aspiration all at once. The Tiffany yellow diamond also highlights how yellow can be celebrated rather than judged, turning what some once called a tint into the entire point of the stone. Diamonds have been used as symbols of power for centuries, long before modern jewelry stores. Diamonds served as visual shorthand for authority, durability, and wealth that could be carried on the body. Rulers used them to announce status in courts, where appearance was a form of politics, and where a crown or brooch could speak before a person said a word. Diamonds also became tools of diplomacy, given as gifts meant to bind alliances or impress rivals, because a rare stone can feel like a promise that cannot be easily matched. What makes this history so gripping is that the diamond's physical traits amplify the symbolism. A gemstone that resists scratching and holds its shine becomes a natural metaphor for permanence and control. Portraits, ceremonial clothing, and official regalia often leaned on that metaphor, building an image of unbreakable rule. Yet the stones outlast the regimes that used them. A diamond can sit quietly in a museum after centuries of being displayed as proof of supremacy, reminding us that power is temporary, that the objects used to advertise it can endure. The symbol survives even when the meaning changes. The modern engagement ring tradition was shaped heavily by marketing. The idea that a diamond ring is the default symbol of engagement feels ancient, but much of its global reach is modern. In the early 20th century, diamond companies faced a practical challenge. They needed more people to see diamonds as essential rather than optional. Advertising stepped in to connect the stone with romance, commitment, and social expectation. And that message spread through magazines, films, and cultural repetition until it began to feel like tradition. The result is one of the most successful stories ever sold because it turned a product into a rite of passage. What makes this fascinating is not cynicism. It is the power of narrative. A gemstone that already had rarity and beauty was given a new role, and millions of people adopted it not because of geology, but because of shared meaning. Over time, the marketing became invisible, absorbed into custom. Understanding this does not erase the emotion of giving a ring. It simply reveals how culture is built, one repeated message at a time, until it becomes the background of everyday life.
Diamond cutting became a science of ingots, not just craftsmanship.
For centuries, cutting relied on trained hands and hard-earned intuition. But eventually, people began to measure what the eye loved. In-like behavior could be studied and proportions could be calculated, which changed cutting from a purely artisan tradition into something closer to optical engineering. A key moment came when researchers analyzed how angles and facet relationships affect brightness, contrast, and fire, helping explain why certain shapes looked lively while others looked dull. That shift did not replace artistry, it sharpened it. Cutters could still make choices, but they could now justify those choices with geometry and light paths, rather than only experience. This is why modern cutting often begins with planning, diagrams, and careful prediction before a wheel ever touches the stone.
The diamond becomes a project with constraints, where every fraction of a decision affects how light returns to the viewer. The fascination is that beauty can be quantified without being reduced. The science does not make diamonds less romantic, it makes the romance more precise, showing that sparkle is not luck, it is design. Laser cutting now shapes diamonds with astonishing precision.
Markings so small, they can be used for identification without changing how the diamond looks to the naked eye. This combination of technology and tradition is what makes modern diamond work feel almost futuristic. The same crystal that formed deep underground can be shaped with beams of light guided by computers, turning an ancient object into something finished with contemporary precision. It is a meeting of timescales. The diamond is old, but the hands shaping it now encode machines that operate at speeds and accuracies no human could match alone. Tiny diamonds are used as abrasives in saws and drills. Most diamonds mined and manufactured are not destined for rings. They are destined for work. Small diamond grains are bonded onto cutting tools because they can grind, saw, and drill materials that quickly destroy ordinary abrasives. Concrete, stone, advanced ceramics, and tough metal alloys can be shaped efficiently when diamond grit does the scratching, especially in industrial blades and drilling bits. This is where the diamond's reputation becomes practical. It is not about sparkle. It is about endurance under friction, heat, and constant contact. The world around you is full of places where diamond has quietly touched the outcome. From construction sites that cut through rock to workshops that shape glass and precision parts. This use also explains why diamond can be both precious and common, depending on quality and purpose. A gen diamond is rare in a specific way. Industrial diamond is widespread in function, and it keeps modern infrastructure moving. There is something grounding about that. The same material used in a proposal could also be used to carve tunnels, polish lenses, and build the physical world. Industrial diamonds are more common than gem-quality stones.
Most diamonds never get a velvet box, because nature makes far more rough material suited for work than for sparkle. Gem quality demands a rare alignment of clarity, color, and crystal shape, while industrial diamond can be clouded, misshapen, or full of internal features and still be incredibly useful. This is why the diamond story has two parallel worlds. One is boutiques and heirlooms. The other is factories, labs, and construction, where nobody cares how a diamond looks, only what it can do. Industrial diamonds can be crushed into grit for grinding and lapping, pressed into wire drawing dies that shape metal with relentless precision, or used to machine ceramics that would destroy ordinary tools. The quiet twist is that this practical diamond world is the larger one. The gemstone is the celebrity. The industrial diamond is the workforce doing invisible jobs that make modern manufacturing possible, then disappearing without applause.
Diamond coatings can protect tools from heat and wear. A thin diamond coating can turn an ordinary tool into something that behaves like it borrowed armor. When diamond is deposited as a film on cutting edges, the surface becomes intensely resistant to abrasion, and it sheds heat in a way that helps the tool stay stable under punishing use. This matters in jobs where a tool is asked to cut hard materials repeatedly without losing its edge, such as machining composites, advanced plastics, or tough alloys that chew up metal. The coating also reduces friction, which can mean cleaner cuts and longer tool life. What makes this so fascinating is the scale. We tend to think of diamond as a chunky jewel, but here it becomes a skin, sometimes only microns thick, bonded to a shape that might fit in your palm. It is diamond used as a material science solution, not a symbol. And it proves the substance is not only about brilliance.
Diamond can be practical, protective, and quietly transformative when applied as a functional surface.
Diamond windows can handle harsh environments in science equipment. Some experiments need a window that will not flinch. Diamond can be used as a transparent barrier in systems where other materials would scratch, crack, fog, or fail, especially when pressure, heat, or corrosive conditions are involved. In certain high-intensity instruments, a diamond window can protect sensitive components while still letting light or radiation pass through, allowing observation without sacrificing durability. The beauty here is not decorative. It is the elegance of a clear shield that stays clear. Unlike softer materials, diamond resists abrasion from airborne particles and can survive cleaning methods that would ruin delicate optics. It can also tolerate environments that would distort ordinary glass, making it useful in specialized scientific and industrial settings.
There is something quietly thrilling about this.
A gemstone associated with romance becomes a literal viewing portal for extreme science. A transparent wall that holds back chaos while allowing measurement to continue. It turns a diamond into a tool for seeing. Diamond is used in high-power electronics to move heat away fast. Heat is the silent enemy of electronics, and in high-power devices, it can build up faster than it can escape. Diamond offers a rare advantage because it can spread heat quickly, pulling it away from hotspots before they damage performance. In advanced systems, diamond can act like a thermal highway, moving energy out of delicate regions and into heat sinks designed to release it. This is not about shine, it is about survival. Devices can run more reliably when heat is managed well, and diamond's thermal behavior makes it a tempting material for demanding applications where every degree matters. The fascinating part is the contrast.
A diamond in a ring is chosen for how it handles light.
A diamond in electronics
is chosen for how it handles heat. The same crystal can serve two completely different human needs, both rooted in physics. It is a reminder that diamonds are not only pretty, they are engineered by nature to move energy in remarkable ways. And modern technology is learning how to use that. Diamond anvil cells squeeze materials to mimic deep earth pressures. A diamond anvil cell is a device that uses two diamonds to crush a tiny sample between their tips, creating pressures so intense they can simulate conditions far beneath Earth's surface. The diamonds are used because they are hard, stiff, and transparent, which means scientists can pressurize a sample and still observe it with light, lasers, or other probes. The sample might be a speck of metal, a crystal, or even a fluid trapped in a microscopic chamber no wider than a grain of dust. Then the pressure climbs until matter begins to behave differently, changing structure, changing properties, sometimes becoming something entirely new. The wonder is scale. You can recreate deep planetary conditions on a tabletop using diamonds as the machinery. It turns gemstones into scientific tools that let us explore worlds we cannot reach, not by traveling downward, but by bringing the pressure upward into the lab. In that moment, diamond is not an object of luxury. It is a bridge to the deep. Those cells helped reveal how matter behaves under crushing force. When pressure becomes extreme, familiar materials can stop acting familiar. Crystals can rearrange into denser structures. Metals can change how they conduct. And even simple compounds can become unexpected phases that do not exist at ordinary conditions. Diamond anvil experiments have made it possible to watch these transformations. Mapping how matter shifts when squeezed beyond everyday experience, this matters for understanding planets because pressure shapes everything in sips in Earth's mantle, to the possible compositions of distant worlds. It also matters for physics and chemistry, because pressure can force atoms into new arrangements that reveal hidden rules about bonding and stability. The compelling part is that pressure acts like an added ingredient you can introduce to almost any material. Rather than blending chemicals, you compress matter into entirely new states. Diamond makes this possible because it can exert immense force while staying transparent enough for scientists to observe what is happening inside the confined sample. It is a quiet revolution created by two crystals pressing on something smaller than a pinhead. Some diamonds are also used to produce ultra-sharp surgical blades. Diamond can be formed into edges so fine they approach the limits of what cutting can be. In certain surgical settings, diamond blades allow extraordinarily precise incisions, which can be crucial in delicate procedures where control outweighs speed. The appeal is not that diamond is magical. It is that it can hold an edge with exceptional sharpness and maintain it without deforming the way softer materials might. That precision can reduce tearing and improve the cleanliness of a cut in certain applications. These tools are not common in everyday surgery, but they exist as a reminder that diamond's usefulness extends into places most people never associate with gemstones. The thought is almost surreal. A material celebrated for romance can also become an instrument of careful medical work, shaped not to sparkle, but to slice with microscopic accuracy. It is still carbon, it is still crystal, but in this form,
It becomes a tool that interacts with the human body in a way that is intensely practical and quietly profound. Diamond quantum defects can act like tiny sensors. A diamond can hold a kind of built-in laboratory inside its crystal, created by small imperfections that behave in surprisingly useful ways. Certain defects where an atom is missing or replaced can respond to their environment by changing how they interact with light. That response can be measured, turning the defect into a sensor small enough to fit inside the diamond itself. Scientists can use these defects to probe conditions at tiny scales in ways that feel almost like giving the crystal a sense of touch. The wonder is that this sensing ability comes from imperfection, not purity. The diamond is valuable not because it is flawless, but because its flaw is stable, repeatable, and readable. It is a reversal of the usual gemstone story. Instead of hiding the defect, you cultivate it because it becomes the feature that makes the diamond useful. This opens doors for advanced measurement in physics and material science, where the ability to sense at small scales can reveal patterns that would otherwise remain invisible. Certain diamond defects can sense magnetic fields at small scales. Some diamond defects can be used to detect magnetic fields with extraordinary sensitivity, even across tiny distances. The idea is that the defect's quantum state shifts in response to magnetism, and that shift can be read out using light, effectively turning a microscopic point inside diamond into a magnetometer. This is captivating because magnetic fields are usually invisible. We infer them from compasses, motors, and electronics, but we rarely see them measured in such an intimate way. With diamond-based sensing, researchers can map magnetic behavior in small devices, study materials that have unusual magnetic properties, or explore biological and chemical systems where weak fields matter. The diamond becomes a quiet observer, stable and robust, able to sit close to a sample without being easily disturbed. It is also a reminder that diamonds can be high-tech without losing their sense of wonder. A gemstone can be a measuring instrument. Carbon can become a detector. And a tiny defect, often invisible to the naked eye, can be the part that gives the diamond its scientific voice. Diamonds can carry measurable strain patterns from their violent journey upward. A diamond's trip to the surface can leave behind a kind of internal stress signature, like tension frozen into the crystal. Under specialized imaging, these strain patterns can appear as bands or zones that reveal where the lattice was squeezed, twisted, or stretched during transport and later history. This is not the same as a visible crack or inclusion. It is more like a hidden pressure map locked into the structure itself. For scientists, these patterns are clues about the forces diamonds experienced inside rising magma and about the events that shaped them. After formation. For anyone else, the fascination is emotional. It means a diamond can carry evidence of trauma without looking damaged, a physical memory of the earth moving fast and hard. The stone may look calm and polished, yet inside, it holds a record of stress that can be measured and interpreted. It is one more way diamonds act like archives. They do not only tell us where they came from. They can hint at what they endured on the way here. A diamond's surface can show triangular etch marks from chemical attack. These tiny triangles are not decoration. They are the diamond's travel scars. In the deep, hot plumbing that carries diamonds upward, reactive fluids can nibble at the crystal surface, dissolving it in a way that follows the diamond's internal geometry. Instead of random pitting, the surface can develop crisp, triangular patterns, like nature used to stencil. Geologists love these marks. because they hint at what the diamond experienced after it formed, not just where it was born. They can suggest interaction with aggressive melts, changes in temperature, or episodes where the diamond lingered long enough for chemistry to leave a signature. For collectors, the fascination is that these marks are evidence of a life before polish. A rough diamond with edged triangles is telling you it was not simply carried upward like cargo. It was exposed, tested, and modified on the way. Even when those marks are removed during cussing, their existence reminds you the diamond has already been shaped by forces that never cared about beauty. Some rough diamonds look greasy or frosted before polishing. Before any cutting wheel touches them, many diamonds look nothing like the finished idea in your mind.
Some appear hazy, as if the surface has been lightly sanded. Others show an odd, greasy sheen that seems to swallow sharp reflections instead of throwing them back. This can happen for several reasons, including surface texture from their geological journey, microfeatures that scatter light, or coatings and residues that cling after time in rock and soil. The shock is that a diamond can be genuinely valuable while looking almost unimpressive in rough form. That is why buying rough is so tricky, and why experienced eyes are prized. The promise is hidden inside, waiting for the surface to be removed and the crystal to be shaped into a geometry that reveals light behavior. This also makes the transformation feel dramatic. A stone can go from cloudy pebble to crisp brilliance without changing what it is, only how it presents itself. Rough diamonds teach a quiet lesson about perception. The most extraordinary things do not always look extraordinary at first glance. Polishing diamond requires diamond powder because little else works. To shape a diamond, you often have to enlist other diamonds. Polishing is not gentle rubbing. It is controlled abrasion, and most materials are simply too soft to scratch diamond effectively. So cutters use diamond grit or diamond powder on a spinning wheel, letting countless microscopic diamond particles do the work, one tiny scrape at a time. The process is slow, deliberate, and strangely intimate, carbon shaping carbon. It also demands skill, because a diamond does not polish the same in every direction. Depending on the crystal orientation, some directions resist more and some yield more easily, which can affect speed and finish. The cutter is not only removing material, they are coaxing the surface into a mirror that will handle light predictably. That is why polishing is often where a diamond becomes convincing, where the surface stops scattering light and starts guiding it. There is something poetic in the idea that the hardest natural gemstone is best refined by its own dust. Like a self-contained craft tradition written into physics, diamonds can be treated to change color, so disclosure matters. A diamond's color can be natural, but it can also be encouraged. Treatments exist that alter how the crystal absorbs light, sometimes turning an unwanted hue into something more marketable, or creating vivid colors that would be rare in nature. This is not inherently bad, but it changes the story of the stone, and that story affects value, collectability, and trust. Disclosure matters because a buyer deserves to know whether they are paying for rarity created by geology or appearance created by a process. It also matters because some treatments are stable, while others require care in repair and setting work. A treated stone can behave differently under heat or during certain procedures, which makes transparency important for jewelers too. The deeper fascination is how this blurs the line between nature and craft. A diamond is already a product of extreme conditions, and now humans can earn a second set of conditions that reshape its look. That does not erase wonder. It adds a new layer of responsibility.
The diamond world becomes not only about beauty, but about honesty, documentation, and choosing which story you want to wear. High-temperature treatment can turn some brown diamonds colorless. Some brown diamonds carry their color because the crystal structure was distorted by stress, leaving the lattice slightly misaligned. Under carefully controlled high-temperature conditions, that internal disorder can be reduced, allowing the stone to appear lighter, sometimes dramatically. So the goal is not to paint over the diamond, but to rearrange what is already there, nudging the crystal toward a different optical behavior.
This can take a diamond that once looked warm or smoky and move it closer to the colorless range many buyers crave. The fascination is that the change is not superficial. It is an internal reset, using heat to help the diamond structure settle into a new arrangement. It also shows how sensitive diamonds are to their hidden architecture. Tiny shifts in the lattice can change a stone's entire presence. For the market, it again returns to disclosure, because a transformed appearance has a different meaning than an untouched one. For storytelling, it is remarkable. A diamond can carry a history of deep stress, then later be given a second chance at clarity through human-controlled conditions. It becomes a gemstone with an edited chapter. Irradiation and heating can create vivid greens, blues, or yellows. Some treatments work by creating tiny changes in the diamond's crystal, forming what are called color centers, places where defects affect how light is absorbed. Irradiation can introduce those defects, and subsequent heating can adjust them, stabilizing the color or shifting it into a different range. The result can be striking hues that catch the eye immediately, sometimes brighter than most natural equivalents. What makes this fascinating is that the diamond becomes a kind of canvas for physics. You are not adding pigment. You are changing how the crystal handles energy and light at the atomic level. This is also why careful identification matters, because treated colors can be beautiful and perfectly suitable for jewelry. But they do not carry the same rarity story as naturally vivid, fancy colors. These processes can also influence how a jeweler approaches repairs, since certain conditions might affect treated stones differently. For a viewer, the wonder is that diamonds can be transformed into new colors through invisible structural tweaks.
A clear crystal can become a vivid statement not through dye, but through controlled change inside the lattice. Moisite can outsparkle diamond, yet it is a different mineral. Many people assume the most sparkle must mean diamond, but moisite can throw even stronger rainbow flashes under certain lighting. That extra fire comes from how moisite bends and spits light, which can make it look almost electric, especially in bright spotlights. The twist is that moisite is not a diamond substitute in the geological sense. It is silicon carbide, a different material with its own structure and personality. In jewelry, moisite can be a deliberate aesthetic choice rather than an imitation, especially for people who love bold, colorful flashes. It also has a story that adds intrigue, since natural moisite is extremely rare, and most jewelry moisite is lab-created to high-quality standards. For diamond lovers, the comparison can be eye-opening. It proves that sparkle is not a single thing. It is a mix of brightness, contrast, and fire. And different materials emphasize different parts of that mix. Seeing moisite beside diamond is like hearing two instruments play the same melody with different tones. One is crisp and white, the other is more colorful and dramatic, and the difference is unmistakable once you notice it. Cubic zirconia looks similar, but it handles heat very differently. Cubic zirconia can mimic diamonds, look surprisingly well to an untrained eye, especially when it is new, clean, and expertly cut. But under heat and wear, it behaves differently, and that difference matters in the real world of jewelry repair. Tours use heat in common procedures like retipping prongs and resizing rings, and some simulants can be damaged, clouded, or even cracked if treated like diamond. Cubic zirconia is also softer than diamond, so it can accumulate surface scratches over time that dull its crispness. This is why a stone that looks brilliant in a display case can lose its crisp presence after years of everyday wear, while a diamond surface resists that kind of slow haze. What is fascinating is how a similar appearance can conceal two very different material realities. One stone is a hard crystal that can tolerate many harsh conditions. The other is a look-alike that requires a more delicate touch. Understanding this is not about disparaging cubic zirconia. It is about recognizing that gemstones are more than visual appeal. They are engineering decisions, and how a stone responds to heat can determine whether a piece of jewelry ages gracefully or demands frequent replacement. A diamond certificate is a map of its specific features. A grading report is not just paperwork. It is an identity card. It records measurements, cut assessments, color and clarity grades, and often a plotted diagram of inclusions and internal characteristics that make the stone recognizable. In many cases, it also lists how the stone behaves under specialized tests, helping distinguish natural from lab-grown, and noting things like fluorescence. This matters because diamonds can look similar in a tray, yet each one has its own measurable fingerprint. A certificate lets buyers compare stones with more confidence and helps jewelers verify what is being bought, sold, insured, or reset. It also becomes important over time. If a diamond is lost, stolen, or swapped, documentation helps establish continuity. The deeper fascination is that a diamond, an object often treated as purely emotional, also belongs to a world of meticulous record-keeping. People fall in love with a stone's sparkle, then anchor that love in data and diagrams. The romance is matched by a map. It is a modern way of saying, this is not just any diamond. This is this diamond. Diamond fluorescence can make some stones look hazy in sunlight. Fluorescence means a diamond emits visible light under ultraviolet, often a bluish glow. In many diamonds, that glow is subtle and harmless, sometimes even flattering. But in a small number of stones, strong fluorescence can interact with bright daylight in a way that softens contrast, making the diamond appear slightly milky or hazy. What makes this so intriguing is that the effect is not constant. A diamond can look crisp indoors, then change character outdoors, as if it has a daylight mood. This is why fluorescence is evaluated carefully, and why two diamonds with the same grade can feel different in real life. It is also a reminder that diamonds are not static objects. They respond to their environment, and light is an environment. For some buyers, fluorescence is a bonus because it can make a faintly warm stone look cooler. For others, it is something to avoid if it risks that hazy look. The fascination is the unpredictability. A diamond is not only about what it is, but about how it behaves when the world changes around it. As we come to the end of our gentle journey tonight, it is worth pausing with the feeling that diamonds leave behind, not as jewelry or status, but as quiet travelers from places far beyond our reach. We wandered through stories of pressure and time, of carbon learning to hold itself together in the dark, of stones that remember oceans, mountains, heat, and force. Each diamond carried a different chapter, shaped by deep movement, sudden ascent, careful hands, and human meaning layered on top of ancient matter. Taken together, they form a calm reminder that the Earth is always working, even when it appears still. Beneath our footsteps, processes unfold, slowly and patiently, creating objects that may one day surface and catch the light, or simply continue resting where they formed.
There is comfort in that scale, in knowing the world is larger, older, and steadier than our daily worries. If you've enjoyed this gentle journey and you're still awake, you're welcome to continue on with the next video waiting on your screen. And if these moments of calm curiosity bring you comfort, you can like, subscribe, or leave a thought below to help other gentle journeys find their way here too. But for now, there's nothing else you need to do. Let the images fade. Let your breathing soften. Allow the sense of depth and quiet time to settle into stillness. The pressure eases, the light dimmens, and the world can wait until morning. Sleep well, and good night.